Hello, 1520, Lab 4, Kinetics. So we have a reaction and we want to determine the orders of reaction with respect to each reagent and also determine the rate constant K. Now you guys have heard in lecture how to do so. There are two approaches. The initial rate approach, where you're measuring the reaction rate right at the beginning, because at that point you know what the concentrations are. And then the integrated rate approach, where you profile the whole reaction and then process the data to determine the orders of reaction and also the rate constant K. It so happens that the initial rate is initial rate approach is generally easier. So we have the decomposition of H2O2, hydrogen peroxide. That's what we're looking at, and we are using a thermochemical approach. So we need to determine first the enthalpy of decomposition of hydrogen peroxide and also the orders of reaction. In this case, we're going to use a catalyst, potassium iodide, because ordinarily that reaction is really slow. And so we'll determine the order of reaction with respect to Ki and also H2O2. H2O2. So, given the reaction that in this case hydrogen peroxide goes to H2O water and oxygen gas, the number of ways that can be done in order to profile the reaction. You could measure the volume of oxygen produced with time. That would work. Yeah. You could measure the pressure if you are operating in a closed system with time. That works. You could, if you knew how, determine the concentration of hydrogen peroxide with time. Yeah, can do that. You can measure the temperature with time. Yeah, and that turns out to be so much easier. And so we'll do that. Easy is good. All right, moving along, my friends. So there is a reaction that I talked about, and it turns out here's the oxygen we were talking about earlier on. I don't know if I can pick up a pen here. Pointer options, pen. Aha. So that reaction is slow ordinarily. Your hydrogen peroxide you buy from the store, 3% stays for a while before it's done. And so we're going to use a catalyst to speed up the reaction. And so our catalyst is Ki, and so the reaction is the same. So how does that work? We're going to measure the temperature with time. And so we start measuring the temperature, and then we add the last reagent, and we recognize here, this is actually a real plot. See how linear it is. And that's at the beginning of the reaction. And so the slope must be what we're looking for, because that is related to the rate of reaction. If the reaction produces more heat, then the slope would certainly be higher. So it turns out in this case that here's our slope that we're going to measure. Degrees centigrade per second. In our case, we're going to use 5 milliliters total volume of our reaction solution. If it's 5 milliliters, density is 1.0 grams per milliliter. And it turns out we can treat this as water and then determine the heat capacity of our reaction system. So 5 grams or 5 milliliters of water, that works out to be 20.9 joules per degree centigrade, if we think of it as just water, and in this case, that doesn't introduce too big an error. And this is described properly step by step in the manual. And then if we divide by the enthalpy, make sure this is joules per mole, and then the volume here, 5 milliliters, which is 0.005 liters, we get the rate of decomposition of hydrogen peroxide. So experimentally, we need this value here, and we need that one, and then we can perform the calculation. Moving along. Yeah, okay, yep. There it is. There it is. All right. So here is the specific heat that I was talking about, and that's the 20.9 joules. For the enthalpy, of course, we need to determine the moles of H2O to decomposed in order to find the enthalpy of the reaction. I'll profile that later. Moving along. All right, so there is our experimental system, quite simple. Here's our data logger, and here is a small temperature sensor that goes into a reaction chamber. There's a little plastic in here, and then this is a styrofoam, obviously, to sort of just keep all the heat in. Certainly, we don't want the heat, want it to stay there, and so we can measure how much heat is produced by the reaction. All right, for the enthalpy of decomposition, same setup as before in the previous slide. We'll add 4.75 milliliters with our auto pipetter of 1 mole of Ki. This is quite a high concentration for Ki. That's the catalyst. And then we'll start measuring the temperature at this sensitivity here, quite sensitive. Then we'll add 0.25 milliliters of 15% hydrogen peroxide. Now all the reagents are in, the reaction starts going, and we just measure the temperature to the end. And so in the end, we will have something that will look like this: baseline temperature, rise after adding the hydrogen peroxide, then flat at the top there. We want the temperature here, want the temperature here, so we can determine the change in the temperature. And knowing the heat capacity, 20.9 joules per degree centigrade, and then calculating the number of moles in this 20.25 milliliters of 15% hydrogen peroxide, we can then calculate the energy produced per mole decomposed. Life is good. Moving along. So here's how we will perform the reactions in order to determine the orders of reaction. Here is a generalized equation. Here's the K. Here's hydrogen peroxide raised to the order of reaction H. Here's the iodide raised to the order of reaction I. If we keep the hydrogen peroxide constant as we compare the various runs, then this just becomes a constant, and we're looking at the variation with I. So if we double the I and the rate doubles, then we know I is 1. If we double the concentration of I, of the iodide I minus, and the rate goes up by a factor of 4, then we know I is 2. Same thing for the hydrogen peroxide. So here's a profile of our runs. I put this one here just for comparison's sake. Really, you don't have all the reagents, and so nothing happens. In this case, we are keeping constant the volume added of the 15% hydrogen peroxide. So that's a constant there. And then we are varying. Remember, these are different runs. From one run to the end, then another run, and here we are varying here the concentrations or the volumes of the 0.25 molar Ki added, and then we'll compare the reaction rates. How does run 2 compare to run number 3? Run 2 compared to run number 3. At that point, we've doubled the concentration of the Ki. Does the rate double, or does it go up by a factor of 4? Moving along. Okay, let's see. Won't move up. Okay, so in the other run, we keep the Ki the same, 3 mils, and we vary the hydrogen peroxide. Of course, here we're adding water just to keep the volume, the total volume to be, or the total mass, volume 5 milliliters, mass about 5 grams, so that we can compare the rates easily. So of course, that first one is a dummy run. So really, we're actually doing a total of 8 runs. There is it says enthalpy there, but in this case, of course, it's the same reaction system for the enthalpy and reaction rate determination. So in this case, for each of the 4 runs, you just add the reagents there minus the critical last reagent, start measuring the temperature, add the reagent, measure the slope. Actually, the data logger, it's pretty good. It actually gives you the slope. So you don't have to figure that out. It gives you the slope. And then 1, 2, 3, 4, and you're done with your runs, and you go to the next set for a total of 8. All right, so let's think through the calculations here. Our stock solution for this part is 0.25 molar Ki. Our hydrogen peroxide is 15%. Can determine the density of the hydrogen peroxide, and it's in my case 1.037 grams per milliliter. From the fact that this is 15%, you can actually determine the concentration of the hydrogen peroxide as a 15% solution, and you should find that to be 4, in this case, that's my number there, 4.575 molar. All right, and for the enthalpy composition, you should find a number close to minus 90 kilojoules per mole. In one of my runs, I found minus 87.8 kilojoules per mole. So here is our equation then that describes the rate. And for rounds number 2, 3, 4, and 5, you can calculate the concentration of the hydrogen peroxide. Let's do Ki. For the Ki, it is, how do you do that? Well, it's 0.25 molar. And if you add 1 milliliter of Ki and the total volume is 5, you've diluted by a factor of 5. If you go up by a factor of 5 volume-wise for the same starting reagent, you've diluted by a factor of 5. So anyway, you can calculate these concentrations here. And just for hypothesis testing sake, we'll also determine Ki squared. That is, we'll investigate whether the reaction is first order or second order. For this calculation of the rate here, here is the equation, right? This is 20.9. This is the slope that will come from here, from your measured with the data logger slope. This enthalpy here that comes from there, be sure to multiply it by 1,000. So this must be positive. That's what these absolute things mean. So make sure this is not in kilojoules per mole, but joules per mole. The volume is 0.005 liters, and then you can perform the calculation for each of the runs. Life is